All right, welcome to lecture video number 1 here in General Chemistry, Chem 105. This video is all about some of the fundamental laws and some of the fundamentals of matter and energy. So let's get right into it. So we are working here out of chapter 1, and chapter 1 is kind of your basics of chemistry. This is a very quick setup and kind of getting us into some of the fundamentals that you probably should know from your high school experiences. But we're just going to kind of reinforce them and make sure that we're all on the right page. So let's start off with some of the base definitions of chemistry. So when we talk about chemistry, what we are really talking about is the ultimate study of the composition, the structure, and the properties of matter, and of energy that is either consumed or given away when matter undergoes some kind of process, some kind of change. Now, inside of that definition of chemistry, what we are looking at is matter and energy, which are the two topics of today's lecture. Now, what is matter? Well, matter is simply anything that occupies space and has mass. So pretty much anything tangible, anything physical is classified as matter. Now, what is mass? Mass is a way of quantifying how much matter is in an object. So the more matter that is present, the more mass that'll be present as well. The other half of this definition of chemistry, energy, is about the capacity to do work. And so in this capacity to do work, what we are talking about is what kinds of work is being done or is being done to the system as this change occurs. And what we'll find is that there are a number of different forms of energy that can be utilized to describe that work that is being done, just like there are a number of different ways that we can classify matter. Now, also in here, we're going to look at some other concepts that are should be very, very familiar to you already. One of those being the scientific method. Now, scientific method at its base is just it's an approach. It's a problem-solving approach that is utilized by scientists, but really by anybody, as a way of observing phenomena, explaining what those phenomena mean, and furthering knowledge on the phenomenon in general. One of the key attributes of the scientific method is that it involves the development of a testable hypothesis and then a means of experimenting and determining the validity of that hypothesis. And you'll have an opportunity to do some of that on a couple of occasions in your laboratory, especially I think next week. You'll be doing a scientific method lab where you're going to have to make some predictions, design some experiments, draw conclusions, test your validity. Now, inside, one of the key attributes of that scientific method is the hypothesis itself. The hypothesis itself is something that we call tentative and testable. Tentative meaning that it is temporary. We do not expect it to sustain for many, 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 many years. Hypotheses are either disproven over time or they get rolled into a larger theory that is developed to help predict future results. That's a hypothesis. It needs to be tentative and testable. So tentative, again, temporary. We either will disprove it at some point, our hypothesis is incorrect, or our hypothesis is correct and we start to apply it to other areas. We start to roll it in with other observations. We develop a more generalized theory as a result of this hypothesis. The other part here is that it has to be testable. And what we mean by testable is that we have to be able to definitively prove or disprove the validity of the hypothesis itself. Now, one of the things that I like to draw on when it comes to hypotheses overall is I want to impress upon you that a hypothesis answers the question, why? Now, this is an important thing to understand. A hypothesis addresses the question of why. What is the why here? Well, the why here is what we're trying to explain. This is different from what we see in a scientific law. In a scientific law, we are trying to address the question, what? So a scientific law is different from a hypothesis and different from a theory. Theories and hypotheses, again, answer the question why. They're an attempt to explain something. A scientific law in general is addressing the question of what. And in particular, what we are looking at there is the overall question of what happens, what has happened. So again, there's a difference between the two. And the reason I'm hitting on this so hard is because one of the most common things that students get wrong, and this is not just college students, it's not just high school students, this is all the way up into adulthood, your parents, your grandparents, people you know on the street. There is a general thought out there that a hypothesis can turn into a theory and a theory can turn into a law. And that is not the case. That is not true. Hypotheses and laws, theories and laws are answering different questions. Really, really, really good theories don't turn into laws. Really, really, really good theories stay theories as opposed to being disproven. So a scientific law is a generally applicable statement about a scientific principle. Usually we can tie scientific laws to mathematics or equations or some kind of, fundamental truth. And that's what makes them kind of different. So again, hypotheses and theories are answering the question, why? Scientific laws are answering the question, what? They're two different things that answer two different questions. With that said, let's take a look at some of the fundamental laws of chemistry. These are series of observations that we've put together and kind of phrased out in a general statement. That general statement tells us something that is true and does it in a very concise way. So here are three common fundamental laws of chemistry. One of them is called the law of definite proportions. The law of definite proportions tells us that compounds will always contain the same proportion of their component elements. Sounds pretty straightforward. We know that water is H2O. There are always two hydrogens for every one oxygen. That is what the law of definite proportions is telling us. Now, the law of definite proportions is often confused with the law of constant composition because they seem to say the same thing. The law of constant composition kind of gets into two different areas. First of all, one of the ways they'll talk about is the law of constant composition does just this. It says that all samples of a particular compound have the same elemental composition regardless of their source. So it doesn't matter if I get water from steam or water from ocean or water from rain or water from the tap or water from the Wabash River. all of the water in that sample is going to be H2O. Now, there's another phrasing of this law of composition that deals with mass. It says that something to the effect of the elements in a given compound will have the same mass ratio of one element to another. And all that really is saying is that for water, the water is going to be a certain percent oxygen and a certain percent hydrogen by mass, and it's always going to be that way. And that is certainly true. But that's also where we kind of get things confused with the law of definite proportions, because they kind of seem to be saying the same thing. Now, the law of multiple proportions is different from these two entirely. What the law of multiple proportions says is that it is possible for elements to combine in different ratios to form different compounds. But when they do, we will get different compounds and we'll get different ratios of one element to another. But the ratios will always be whole number ratios. So for example, carbon and oxygen will combine to make many different compounds. Two of the more common ones are on your screen there: carbon monoxide, CO, and carbon dioxide, CO2. Now notice in both of these, we have a different ratio of carbon to oxygen, 1:1 in carbon monoxide, 1:2 in carbon dioxide, and that's okay. That's okay. The key there, whole number ratios. It's not 1 to 1.45. It's not 0.97 to 0.14. It's 1:2, 1:1, 3:2, 4:5, whatever the case may be. So let's start looking at matter a little bit more closely. When it comes to matter itself, we can break down properties of matter, that is, things that we can use to describe matter. And we can break it down in a number of different ways. You've probably heard of physical properties versus chemical properties. Well, there's another way of determining properties, and it's based upon composition. Intensive versus extensive. Intensive properties are those that we can observe, and they are the same every time, regardless of how much substance we have. So if I have a small amount of the substance or a large amount of the substance, the intensive properties will always read the same. And these would be things like color, malleability, density, those kinds of things. I can look at this bottle of hand sanitizer here on my desk, and it may not show up so great on camera. This is a light green color. Now, it doesn't matter if I have a whole bottle of it or if I just squeeze a little bit into my hand here. The light green color is going to persist regardless. That's an intensive property. Doesn't matter if I have a lot of it or a little of it, they are always the same. Same thing goes for density. Same thing goes for a lot of different properties. Extensive properties, on the other hand, these are the ones that do depend on the amount of substance present. So we're talking about things like mass. This bottle of hand sanitizer, full of hand sanitizer, weighs more than the little bit that I squeezed into my hand. There was a lot more in the bottle than there was in my hand. That's an extensive property. A lot of your quantitative measurables are going to fall into this category. Things like length, things like volume. But what's interesting is that ratios of extensive properties usually result in intensive properties. So notice here that we had density. Well, we can see that the density is an intensive property, but the things that make up density, mass and volume, are both extensive. Mass divided by volume gives us density. And so it's kind of like the two intensive properties kind of cancel, or the two extensive properties kind of cancel each other out to give us an intensive property as a result. As I mentioned before, most of us are familiar with properties like physical properties and chemical properties. Physical properties tell us how much, or Physical properties can be measured rather by simply observing them without actually changing the substance itself. So we can take an object's temperature. We can measure its density. We can determine when it melts or when it boils. We can determine if it's a solid, liquid, or a gas just by looking at it. Don't have to change anything about it. But chemical properties, on the other hand, those are ones that we do have to have a chemical change take place in order to observe. If I'm going to oxidize something, I'm going to have to do a chemical reaction that forces an oxidation on that substance. When I turn something on fire, when I ignite something, the flammability that comes as a result of that ignition is a chemical property. And the things that happen to that substance because it was set on fire, those are the observables that we can write out as the chemical properties related to flammability for that substance. So chemical properties often come with changes in physical properties along the way. So when something gets oxidized, it usually changes colors. Sometimes it changes form. When something burns, we usually see lots of physical change, lots of physical properties. We see, a change in temperature. We see a change in light. We see a change in color. We also see changes in state, solids turning into gases, liquids turning into vapor, those kinds of things. So lots of times chemical properties will show changes in physical properties, but it's not necessarily the other way. In fact, it's not the other way. Moving on to classes of matter. When it comes to matter itself, we can break matter down into two different categories. There are the pure substances and there are the mixtures. The primary difference between them is coming back to our law of constant composition. Pure substances have a constant composition. Mixtures have what we would call a variable composition. So pure substances are going to have the same appearance in every single particle throughout the entire sample. And so as a result, pure substances are going to have the same physical properties, the same chemical properties throughout the entire sample. The other thing that we need to know about them is that we will not be able to split them into simpler substances physically. Whereas mixtures, well, mixtures involve the combination of many pure substances, at least two. And we can easily separate them by physical processes. Sometimes just as simple as grabbing, one of those substances with your fingers or with a toothpick or with tweezers and separating it from the other parts of the substance. Have you ever gone to a restaurant and it had something in it that you didn't like? You go and you pick out the cucumbers or you pick out the red onions and you put them over here. Well, that's easy to do because a salad is a mixture and the mixture is pretty easily separated physically. You just take out what you don't want, at least in some kinds of mixtures. Let's investigate each one of those a little bit closer. So if I look at pure substances, again, pure substances, we are going to see constant composition reigning supreme there. But what does that mean? How do I differentiate them from each other? Well, in elements, I have only one type of atom. But in compounds, I have two or more types of atoms that are combined chemically in a fixed ratio. So with compounds, we're getting a lot more complicated. We're getting a chemical combination of one atom type to another and a fixed ratio. So that fixed ratio is how we ultimately address the constant composition angle that needs to be measured here. Now, another difference between them, because elements are only of one atom type and not more, We cannot even separate them chemically. The only way to change an element into something else is through some kind of a nuclear process. And those are messy and generally dangerous, and oftentimes require a considerable amount of energy, like what you get in the sun. For compounds, again, we get fixed ratio of one element to another or multiple elements to each other, but we can break them down by chemical means. So decomposition reactions, single plate replacement reactions, redox reactions, these are kind of the reactions that can break down a compound into components. Probably the most common one of these examples of an experiment is where we split water. We take water, we hook it up to electrodes, and we turn on the juice, and it splits the water into hydrogen and into oxygen. And the water has been effectively split into its components as a result. Those are chemical processes. I can separate the components of a compound from each other chemically, but not physically. I have to do a chemical reaction of some kind to get it to work. Mixtures, on the other hand, mixtures we're getting into, we know that they have a variable composition. Which means that they are capable of taking a variety of different forms and still being considered mixtures. The example I like to give is if you are making lemonade or Kool-Aid or icy, pick your favorite beverage that you can easily make at home. Well, there's usually a few components to it. There's water, there's tea or lemons or drink mix, and then there's sugar. And for the most part, people are pretty good about, okay, I need this much water, I need this much tea, I need this much Kool-Aid or this much lemons. But the amount of sugar, the amount of the ratio of one to another here does change. And it doesn't necessarily change the identity of what we're drinking, but it does change the flavor considerably. If you add a ton of sugar to tea, it's going to taste differently than if you add just a little bit of sugar or no sugar. Now, you still look at that beverage and you still say, oh, that's tea. But what's inside, the ratio of those ingredients to each other drastically change the experience. That's called a homogeneous mixture or homogeneous mixture. We sometimes refer to these mixtures as solutions. The way to tell them apart is they are the same throughout. They have a uniform appearance. By contrast, a heterogeneous solution has a disuniform appearance, meaning that, kind of like the garden salad example I gave earlier, we can easily pick out all of the individual components because they're physically visible to us as different. Once you mix up a batch of iced tea, you can't really easily separate the sugar from the tea from the water. You can do it physically, but it's not very easy. It's going to involve some extra processes like evaporating all the liquid, filtering out the tea leaves, those kinds of things. Whereas a garden salad, well, here's my lettuce, here's my tomatoes, here's my carrots, here's my whatever. And just as quickly as you bring it all together, you could easily separate them all apart again. This last term here, immiscible, when liquids are dissolved into each other, when we try to get liquids to mix with each other, we call liquids either miscible or immiscible. Miscible means they dissolve perfectly well into each other. Water and alcohol are a great example of that. Immiscible means that they don't mix together. Classic example of this is oil and water. So We get to the same kinds of ideas with liquid-liquid mixtures as we do with liquid-solid mixtures or even solid-solid mixtures. Just we have a slightly different name for them. So what this flow chart does is this flow chart kind of gives us kind of a question and answer tree that if I was trying to classify matter and put it into groups, I could answer a series of relatively simple questions and be able to determine, okay, am I dealing with an element or a compound or some kind of mixture? And that's what this flow chart kind of walks you through and does. Last topic that we're going to talk about regarding matter today is the states of matter. As you know, there are 3 different states of matter: solid, liquid, and gas. The primary differences between them are in their arrangements and their spacing. If you go back to the slide here, water is a little bit different in terms of the spacing. In solid phase, it's not quite as dense as in the liquid phase. That's actually kind of unusual. What I want you to point out and look at is as being the fundamental differences here, though. For a solid, we can see that the molecules are close together and that the molecules are arranged in an orderly fashion. Why is that important? Well, that's why solids have the properties that they do. Why do they have a definite shape and a definite volume? Well, the definite volume comes from that close packing. The definite shape comes from that arrangement. Whereas in a liquid, molecules are still close together, but we lose that organization. We lose that orderliness that we saw in solids. And for that reason, liquids are still confined in volume, but they take on whatever shape. That disorder in their arrangement makes it so that they can take on whatever shape the container that they're in takes. And gases, on the other hand, molecules are far apart and disordered. And as a result, they just fill whatever space that they're put into. And so if we take these definitions and put them into place next to the description, we can see what kinds of properties are aligned with which one. So again, the orderliness is impacted by shape. The closeness gives us an idea of volume. So the fact that they have that are close together means they're going to have a definite volume. Their disordered nature leads to an indefinite shape. And then for gases, the fact that the molecules are far apart means that they're going to have an indefinite volume as well. With those phases of matter, there are several different transitions that can occur between those phases. The 6 different transitions are sublimation, deposition, freezing, melting, condensation, and vaporization. The names of each of those are shown here in this diagram. The ones that we're probably the least familiar with are sublimation and deposition, the solid to gas transitions. Otherwise, we're probably pretty familiar with most of these. All right, last bit here, energy. As we mentioned at the very beginning, energy is the capacity to do work. And by definition, work is the force applied over a distance, so force times distance. Now, energy comes in a variety of different forms. Most notably, we think of potential energy and kinetic energy. Potential energy being stored energy, and this is due to either position or composition of a substance. So a pen that is held at one height is going to have greater potential energy than the pen held at a lower height, because the force of gravity acting on this pen is going to act on it longer the higher it is. Compositionally speaking, that gets into the bonding and things. Kinetic energy is the energy of motion. So when objects are in motion, they have kinetic energy as part of them. Now, those are the two primary types. Other types of energy you're probably familiar with as well. Things like nuclear energy, which is the energy stored within atoms. Mechanical energy, energy stored with machines as machines operate. Chemical energy, which is very closely related to potential energy. So there are lots of other kinds, but they usually fit into one of these categories or the other, or it's sometimes kind of a combination of both. The primary form of energy that we will focus on most in this class is heat. Heat is the transfer of energy due to differences in temperature. Now, those differences in temperature can manifest themselves in a number of ways, but those are the ones that we usually focus on because heat is probably the thing that we are able to measure the easiest when it comes to chemical and physical reactions and processes. Last note that we want to bring in today concerns the law of conservation of energy. What the law of conservation of energy states is that energy is neither created nor destroyed in any kind of process. All that happens in any of those processes is that the energy changes from one form to another. So as I drop my pen from a height above my desk to my desk, energy goes from potential when it's up here. Once I drop it, it starts to convert into kinetic, and it hits the ground, it makes a sound, it generates and transfers some heat to the desk, although a small amount, and that's the end of the process. But if I look at the total energy of the entire area in and around this pen and this desk, what I will find is that the total energy of all of that is the same. All that has happened is that the energy that was given to the pen to raise it up converted into energy that was released as it was falling to the desk. There are other laws of conservation of matter, laws of conservation of mass, and they all kind of follow the same principle that whatever is being conserved can't be created or destroyed in a physical or a chemical process. So be on the lookout for those terms as they come up later in the semester. But that is all for today's introductory lecture to our first concepts of the fundamentals of chemistry. In our second lecture, we will be going over the primary ideas behind units and measurement, which will get us moving toward the end of chapter 1 here. So until that moment, have a good day.